In this video, we're going to introduce the idea of heat capacity. Heat capacity is defined as the ratio of the amount of heat added to an object divided by the change in temperature of that object. So it basically tells you how much heat do you need to add to a system in order to raise its temperature by a set amount. So we write this as Q over delta T. So an example of a heat capacity would say I had some substance, and I could say if I add 50 joules of heat to that substance, I will raise its temperature by 1 Kelvin, right? So then the heat capacity would be 50 joules per Kelvin. We know that the heat is related to the change in the total energy of the object or whatever substance we're dealing with minus the work, right? So the total change in the energy of the object is Q plus W, so Q is the change in the energy minus the work, and then we divide that by delta T. Now, the heat capacity of a substance depends on how you add that heat into the system. And there's only two ways of doing this that we'll think about that are fairly simple. You could allow the volume or the pressure to change in arbitrary ways as you add this heat, and that would complicate your specific heat significantly. So what we're going to do is we're going to consider only the case where we add heat and we don't let the volume change, so specific heat at constant volume, so there's no expansion of the system. And we'll consider the specific heat at constant pressure, which is slightly more complicated to calculate, but it turns out to be more useful in a practical sense. But let's start out with the constant volume. So the idea is that if your volume is constant, then no work can be done on the system. Work is equal to the integral of P dV, change in volume, but if your volume doesn't change, then you're not doing any compression work, right? And we're assuming that there's no types of work being done that aren't compression work either. So we say there's no work done on the system, which means that my heat capacity is just the change in the energy of the system divided by the change in temperature. And we're doing this at a constant volume. So this V here outside tells us what we are holding constant when we do this partial derivative. Okay, the simple example that we have that we can do at the moment is an ideal gas. For an ideal gas, our energy U is given by F over 2 nKT, where again, F is our number of degrees of freedom. And what we can see is when we take this derivative, we just get F over 2 nK. So our heat capacity at constant volume for an ideal gas is given by this relation here. Just a quick note, obviously if I have more molecules in my ideal gas, then it's going to take more energy to heat up all of those molecules, right? So it makes sense that the heat capacity depends on how many molecules I have. It's going to take a lot more energy to heat up, say 10 to the 23 molecules than it would take to heat up 1 molecule. So it makes sense to depend on N. The fact that the heat capacity depends on the number of degrees of freedom also makes sense, because the more degrees of freedom that I have, the more ways that my molecules can store energy. So, for example, if I have a monatomic ideal gas, if I want to heat up that gas, it can only store energy in terms of translational motion, so I just have to make the molecules move more quickly, and that will increase the temperature of my gas. If I have a diatomic gas, where the molecules can both have translational motion and their rotational motion also contributes to their energy, I have to spend energy to speed the molecules up, and I have to spend energy to get them to rotate faster so that the total energy of my system increases by the same amount. And so you end up having to kind of spend more energy to get the same change in temperature when you have more degrees of freedom. So the heat capacity, the amount of heat required to raise the substance by some amount of temperature, increases as your number of degrees of freedom increases. Okay, so this is the equation for the specific heat at constant volume. This is the specific value if you are dealing with an ideal gas. We'll deal with more complex systems later on, and we'll figure out how to calculate the heat capacities of those as well. Now let's turn our attention to the heat capacity at constant pressure. At constant pressure, the gas will both heat up and expand as heat is added to it, right? So we have our term for the change in the internal energy of the gas, delta U, which is going to in turn lead to the gas heating up, an increase in temperature. But we also have the work done on the gas here as the gas expands. So as the gas expands, the environment does negative work on that gas, reducing the energy in the gas. So we have the heat that is going into the gas. Some of it is going into increasing the temperature, our delta U, but some of it is going into doing work on the environment, or having the environment do negative work on the gas as it expands, right? So not all of the heat added to the gas goes directly into raising the temperature of the gas. Some of it goes into that work done on the environment. So we would expect, just without doing any of the math, that at constant pressure, the heat capacity should be higher. It should take more energy to raise the temperature by a set amount at constant pressure, because we're going to be losing some of that heat that we add to the expansion work that the gas has to do as it expands. Okay, so we take this, we are turning our deltas, so we distribute the T to each of the terms individually, and we're turning our deltas into partial derivatives, so we're taking an infinitesimal change in energy here and an infinitesimal change in volume here. And so this is the generic expression for the heat capacity at constant pressure for any substance. The heat capacity of an ideal gas at constant pressure, well, we can again use the equipartition theorem to write the energy in terms of temperature, and then take a derivative of that with respect to T, which gives us, in fact, the exact same result, our heat capacity at constant volume. It's exactly what we did over here. And then we end up with P times the partial derivative of nKT. This is taken at constant pressure. So we're taking this derivative at constant pressure. So the only variable in here is the temperature. And the temperature drops out, and the P in front cancels here, so this is nK. So for an ideal gas, our heat capacity at constant pressure is equal to the heat capacity at constant volume plus nK. As expected, this is larger than our heat capacity at constant volume.